Okay, so hey everyone, and today we're gonna be talking about a very interesting topic that follows the tokenization session, and this topic will gonna be about, or the core of this topic is presenting some papers that were before the era of LLMs. So we're gonna be presenting some of the sequence models, sec-to-sec models, models that understand sequences, but that were presented before transformers and before 2017 in general. This is a recording of a session we did live, but the recording there was a bit jittering and the recording didn't went so smooth. So we've decided to re-record it in order to make it a smooth experience for you. So what we're gonna be talking about today is we're gonna work with some certain type of model called recurrent neural networks, and then we're gonna see an optimization for recurrent neural networks, which is called long short-term memory, or LSTMs for short. Another optimization is called gated recurrent units. Then we're gonna reiterate on NLP and word embeddings concepts. We're gonna be touching on the attention model and a bit about the transformer or motivation for next time. If time permits, we're gonna be talking about some applications. Okay, so some notations, and to motivate our session, we're gonna be referring to an example in which it's name entity recognition. So we're gonna be having a sentence, and for this sentence we're gonna try to make up or build up a model in order to predict if each of the words in this sentence is a name or not. So for Harry Potter and blah blah blah, we're gonna be predicting that Harry and Potter are entities of names and the word and is not. So to be more concrete, our input example is gonna be a vector x that have a number t of x tokens, and those are our input tokens. And for each input vector, we're gonna be having a corresponding output vector, which is the label, which is a y vector with the same length of the x vector, and it's holding a 1 whenever we have in that position a name, and a 0 whenever we have in that position a non-name entity. Okay, and we're gonna try to process this sequence in some neural network. But what model we seek? And before we spoil it out, let's talk about a limitation of the neural network that is vanilla, that is ordinary. So we're gonna have this ordinary neural network here, and we're gonna try to fit this sequence in this neural network. So what are some of the limitations? Well, to design such a neural network, we need to define the hidden layers, and the hidden layer we're gonna be expecting a constant dimension from the input vector. And as we can see here, we are processing sentences, and sentences may be of different lengths. So the first limitation we have is that inputs and outputs can be different in length when we process sequences. Also, the typical neural network does not learn features across the different positions. What I mean by that is when we process some token in a sequence, we may, not all of the time, but we may need to refer to a sequence back in time or forth in time. So when processing a sequence I, a token I in a sequence X, we may need to attend or to refer to other tokens in this sequence. The thing that we don't do in ordinary neural network architecture. So what we're gonna be doing in an ordinary neural network architecture, we're gonna be getting this sequence. In this case, we're gonna process 3 tokens at a time, squash them into a hidden layer. So we're gonna squash all the information into a hidden layer without doing a smart thing to aggregate all the information, just squash them into one layer and then get an output. And the thing that will not let us share features among tokens. The thing that we want is something called or a design called a recurrent neural network. So what we seek from this design is, one, to process sequences of any length, two, to share features and to remember things across the whole sequence when we are processing individual tokens. So let's take an example, and things will gonna be illustrated followingly. So let's say we are processing the token x2. And x2 is Porter. Okay, we're gonna process the token x2 and project it into some layer and compute something called the hidden state or the activation. And you can think of the hidden state as a high dimensional memory that remembers everything from the past. So when processing Harry, I'm gonna be projecting into some layer, then aggregating the information of when processing the token Porter, I'm gonna be projecting it into some layer and then calculating something called the activation, which is dependent on the past tokens like Harry, and then I'm gonna compute this shared activation or this unified activation in which I have the information of Porter and things from the past like Harry. And then I'm gonna do some sort of prediction on the word or on the token x2. So I'm gonna be projecting it into another layer that is responsible for doing the output aggregation. Let's say that again. I'm gonna be inputting x2 into some layer, projecting all the information into some layer via a matrix called WAX, and I'm gonna be computing this thing called activation, which is a shared memory to remember things from the past based on the past things and x2, and then I'm gonna be projecting things into another space via a matrix which is responsible of producing the output, which is called WYA. So input a token, compute some activation based on the past and the token inputted at time t, and then based on this activation make a prediction. And by this we will be solving the two problems. First, we can process sequences of any length, like I can do here x1, x2, x3, and since I'm dealing with one token at a time, I can now my architecture is not dependent on the length of the sequence, and I can aggregate features over tokens. So when processing x3, the activation A2 that I'm using to compute the activation A3 and then compute the answer now have the knowledge of x2 and x1. So when doing every prediction will gonna be dependent on two things, the input and the past. To take a deep dive into the math of RNN, I'm gonna be presenting those two equations, and the first one is specific for index 1, but the second two here are the general ones. I'm gonna be jumping to the general ones. So to compute the activation at time t, I'm gonna be projecting the activation from the last timestamp into via some layer, adding to it the information of the token also projected into some layer. So I'm gonna be processing the input and the activation from the last timestamp, adding some bias and activating the whole thing via a nonlinearity. And this is how I compute the activation function, the activation state or the hidden state at time t. This is the memory. It's in terms of AT-1, which is the last memory state or the memory from the last timestamp, and in terms of the input at this timestamp, which is xt plus some bias. And I'm based on this memory, based on this unified information, I'm gonna be using this to compute the output at this timestamp by projecting the hidden state or the activation state via some layer into some space, aggregating all of this via a nonlinearity, and it's gonna be probably be a sigmoid in our case, since we are predicting a 0 or 1, and where we produce the output yt. You can think of a neural network as something getting of a recurrent neural network of something getting the input xt and then doing some computation inside and recurring over the past and then getting the output. Or you can unfold it over multiple timestamps through time, multiple hidden states through time. And the reason why I don't like this representation right here on the right is that this will gonna falls you to think that these are different weights here. No, this is a replica over time. At each timestamp, we take the inputs, we compute a unified activation over in terms of the input and the last activation or the last hidden state, and then we get an output based on this activation, which have the information from the input and the last timestamp. Now, let's talk a bit about backpropagation and how we learn in such a network. In our case, we are predicting a 0 or 1 at each timestamp, so our loss at each timestamp will gonna be the cross-entropy loss, which is minus the minus log of the prediction, if we are predicting 1, and if we are predicting a negative example, we're gonna be having a loss of minus log of 1 minus the prediction. And this is just to penalize things out when we have it as probability format. The overall loss will gonna be a summation over all the timestamps, a summation over the losses over all the timestamps, and the gradients should flow backward to the matrix multiplication node where we compute the gradients with respect to the weight matrix and the hidden state. The gradient with respect to the hidden state and the gradient from the previous timestamp meet at the copy node where they are summed up. This sentence will gonna be illustrated right here, and the premise from this slide is to let you know that okay, you don't need to take a deep dive into the actual gradients flowing back, but the intuition is that we're gonna update the weights. The takeaways from this slide is that we're gonna update the weights at each timestamp, and at each timestamp we're gonna be receiving 2 gradients, one from the individual prediction and one from the hidden state that is from the future, the t+1. We're gonna take those 2 gradients and sum them up. Actually, in the session I told you to multiply those up. This is wrong. I looked it up. They sum them up like we do in a neural network when it gets different gradients from the different neurons ahead. Okay, if you want, I'm gonna be sharing with you a document about the actual derivation of RNN. Okay, RNN types are many, and for each one we have its own use case. We have the one-to-one, and this is just a vanilla neural network, one input, one output at a time. We have the one-to-many, which is we have the one-to-many, which is taking one input and generating a sequence. We have the many-to-one, which is taking a sequence and generating just one number, like sentiment analysis. We're gonna be taking a review or a comment from Twitter and predicting if this comment was bad or good, simply. We have a many-to-many, like our example from the name entity recognition. We're gonna be take a sequence, and for each token, predicting that if it's a name or not. This is a many-to-many. And we have another variation of a many-to-many, which is an encoder-decoder based. This is used in machine translation, where we input all the sequence into one neural network, and then we get a representation of the full sequence. We pass this representation to another network called the decoder, and we start generating a sequence from the other language. We're gonna take a deep dive into this in a bit. Okay, but using this method to backprop into the RNN will gonna result in one problem within backpropagation. So within backpropagation, we have two main problems. The first that we can that we can that we can that we can get. The first is vanishing gradients, and the second is exploding gradients. Exploding gradients is where we have big gradients updates, and we can easily spot this by setting a threshold for the gradients. And we have a vanishing gradient where it's a very tricky thing to spot, and it prevents you from the full learning objective for your machine learning problem. So in backpropagation, we fear vanishing gradients, since we need to backprop and do chain rule over time. And what if our sequence was too big? The gradients will gonna be too small, and we're gonna suffer from updating the weights matrices in a good format. So what we do is, instead of computing the activation at each timestamp, and sometimes you have a token that's meaningful, that's meaningless. Sorry, like the token the, or and, or. So instead of computing the activation at each time and adding the overhead of computing the gradients for the new activation, we're gonna just make an algorithm or make a proxy when we need to update the activation and when we don't. And by using this, okay, so if we pass the same copy of the activation, we don't need to, the two copies will gonna be receiving the same gradient, so we will be saving one operation of chain rule. Okay, thing is, we're gonna let the neural network decide when it needs to update the activation and when it doesn't. For this, as usual, we're gonna compute C tilde, which is a candidate for being an activation at time t, using the same process as always, aggregating the information at time t and the information from the previous timestamps. And then we're gonna be outputting or learning a parameter, a one number output called update gate, and this update gate is signal activated, so you can think of it as 0 or 1. And then we're gonna at each timestamp decide if we want to update the activation, the hidden state, or we want to keep the old one. So at each timestamp, CT, or the activation at time t, is either gate C tilde, and in case of the gate was 1, we're gonna update it, so 1 times C tilde plus 1 minus 1, which is 0, CT minus 1. In case if the gate was 0, we're gonna throw the C tilde and then keep on the activation or the hidden state from the last timestamp, and keep CT minus 1 as the activation at this timestamp. So that's the full gated recurrent unit algorithm, in which we decide when we need to update and when we don't need to update our activations or hidden state. This will gonna solve for us the backpropagation through time vanishing gradients algorithm, and in order to do this, we need to backpropagate over the full sequence, and for this, we're gonna be chittering out of this problem. We have another variation of this optimization that works exactly the same, which is called long short-term memory, or LSTM. So compared to GRU, LSTMs are much older, but they are computationally expensive. So people used to create an optimization for LSTM, which is gated recurrent units. So it's the same idea and the same problem we're trying to solve. We're trying to figure out when we need to update the activation or the hidden state and when we don't. So also we keep it to the network to decide, but using 3 gates. So we compute a candidate gate as usual, and then we compute 3 gates: update, forget, and output. And then we try to update or not using the update and forget gates, and we try to scale how much we need from that chosen gate. Hidden state. So we decide to update or forget, and then we decide how much we need to get from this updated gate. Okay, and now we should be talking about a variation of the RNN, which is called BRNN or bidirectional RNNs, in which sometimes we don't need just to remember things from the past, but we need to pay attention or remember or take a look to the future. When processing a sequence x1, x2, x3, x4, when processing exactly x2, let's be specific here, we don't need only to refer to x1. We may need to try to look at things like x3 and x4. So what we do is we make our first pass as usual, computing a1, a2, a3, a4, and then we make a reversed pass, computing a4, a3, a2, a1 again, but from right to left. So the first pass is from left to right, the second pass is from left to right, and then from right to left, and then we get 2 activations, one that's coming from the future and one that's coming from the past. We aggregate those into one activation, and we compute an output based on this new hybrid activation. And then every output will gonna be in terms of the past and the future activation. Also, a variation should be deep RNNs. You may ask yourself at this point how we add layers, how we add complexity for this network. Well, we can add layers of RNNs over layers of RNNs. So basically, the output of one unit can be the input of another unit, and those are 2 layers, and we can add as much as we want from these layers. I'm touching on those variations very quickly, since the idea is to get an overview of the things going around and not to take a deep dive. But the idea is very simple. You can onboard from here as long as you understand the high level picture. Okay, now let me touch on the goal of language modeling. Assume you have a language model, and the language model idea is to generate sequences over English words. The full idea of language modeling is to assign probabilities for sequences that make sense higher than sequences that don't make sense. Like the apple and pear salad is having a 10-15 probability given a language model LM, and the sequence the apple and pear salad is having a better probability, a bigger probability, which is 10-10 given this language model. So the language model is highly likely to make the sequence, this is the second sequence than the first sequence. And this is the full premise or the full goal of a language model. We need to assign change the probabilities or overall probabilities for sequences that make sense higher, that are higher from sequences that don't. And the way this works in the case of RNN, we're gonna just input a 0 token to let the RNN produce probability over a vocabulary, and then we need to sample from this distribution the first word, and then this sampled word is plugged in again in the next timestamp in order to make probability over the same dictionary but conditioned on the one sampled from the last timestamp. So let's say we sampled the first token, the first output token as dogs, we're gonna be re-inputting this into the next timestamp, and then getting the probability in condition, or knowing that we get dogs in the first timestamp. So p dogs, then p average dogs, then p12 conditioned, or knowing that dogs average, so on and so forth, until we sample something called end of sequence, which is a token that we add to the vocabulary to maintain the end of a sequence. And we have also something called SOS, which is start of a sequence, and we have something called unknown for some unknown tokens we process when we are processing the web pages. And now I'm going to be recapping on embeddings. Embeddings are, at the very simple definition, taking one hot encoded token, like the one presented by Basil in the last session, and presenting this in a d-dimensional space, or presenting this in a d-dimensional in a d-dimension vector. So, and the premise is tokens now have something called semantics, in which man and woman have the same distance as king and queen from each others. By this we acquire some semantics. If you look at the TSNE plot to my right, I'm gonna be having the human alike words together, like king, man, woman, queen, and the animals together, like cat, dog, fish, the fruits like grape, apple, orange, and the numbers. And those are clustered together since they have similar embeddings, or they share similar features. The most common property of a word embedding is that they acquire semantics, like the distance from man to woman is the same as king to queen, and the way we measure similarity between two embeddings is the way we measure similarity between two vectors using a cosine similarity metric. And cosine similarity will just measure the cosine angle between the cosine of the angle between those two embeddings. If it's 0, if the angle is 0, the cosine is 1, and it means that the two vectors are aligned. If it's 180, the cosine is -1, and those two vectors are opposite. If it's 90 degree, the cosine is 0, and those two vectors have no meanings. I'm gonna skip this slide, but the main take is that we are trying to process, or trying to get, an embedding matrix E, in which is it's some number of dimensions times the vocabulary. So for every vocab I have, for every vocab I have one column, which is the embedding of this token over a vocabulary, and the way I process it, or get the ith column, is that by multiplying the matrix by the one hot encoding vector to get some embedding I. So the embedding I will gonna be the embedding matrix times the one hot encoded token, and then I get the embedding for the ith token. You don't want to implement this by yourself. There's an embedding layer in Keras, in TensorFlow.keras, to get the embedding matrix. Also, I'm gonna be touching on how to make, or how to train such a network. We do this usually using Word2Vec, and this is a very old technique. We have much newer techniques to do so. Idea is make a hard classification task, and the premise is that we're gonna be learning the embedding weights, or the embedding matrix. So in the first technique, which is CBOW, continuous bag of words, input some context words and try to classify the target, the missing word. So this hotel is very good. We're gonna take out is, make it the target, and we're gonna try to predict is from this hotel very good. And this is a hard task, but the premise is not to do good on this, but to do good on the embedding side. We have also another variation, which is called skipogram. Skipogram will gonna be inputting the target word and try to classify the context. And this is also a very hard task, but the premise is to learn the embeddings. So we're gonna be inputting is and trying to figure out this and hotel, very, and good. Okay, this is just saying what I've just said. In skipogram, we are inputting context word and trying to estimate target words. In CBOW, we try to predict the middle target word based on some context. In both cases, we're gonna just take an embedding, and this embedding is and this embedding is projected into some layer, and doing a softmax to get probabilities, and just sample out of it. And I'm gonna really give you a hint about some engineering tricks done. You see the summation in the denominator of a softmax. This is a very costly summation. To loop around it, what we can do is, instead of doing a softmax, we can do individual sigmoids. So we can augment our data set to make it a binary classification task in which we have the context and the target word, like orange and juice have the label of 1, and then we sample some negative values, like some negative examples like orange and king, orange and book, orange the, and we assign those to a 0 label. Those are not targets to each others, and we try to do a logistic regression. So now we input and now we input the two things, and we get their embeddings, and we input the two things, and we try we input the target word and to try to figure out if it's a target or no for the context word, and by this we promise ourselves that we're gonna have a good embeddings at the end of the training methodology. Also, the way we're gonna be choosing out the words is smart. So we're not gonna just assign target words to any context words, since we're gonna be having a lot of off and there and things that are meaningless. So the probability of having things as a target word or not will gonna be scaled by its frequency. So it has lower probability if it has high frequency. So we loop around taking da and or a lot. Also, we need a way to debias word embeddings. And what's debiasing? Bias is when we get some semantics in the embeddings that are not true, like referring man always to a doctor while woman to a homemaker. This is really bad, and this is bias. We need to take this bias out of the embeddings. So what we do is we have two steps. The first is identify this bias direction, identify this bias vector. To do so, we subtract every two opposite embeddings, like he and she, male and female, grandfather and grandmother, blah blah blah, in order to take one direction of the bias. And having those vectors, those subtracted vectors, we do something like SVD or a simple average can work here, and we get an idea of where's the bias direction in our space. And we know from 218 that the non-biased direction is orthogonal to the biased direction of cosine 1, cosine 90. And what we try to do is to project, or for every word that is not definitional, like doctor and babysitter, we try to get rid of the bias. We try to project them into non-biased direction. I'm not sure about the way, but I'm sure there's an algebra trick for this. I'm gonna look it up and then send it to the group. And then I'm gonna make so the first step is to put things that are not definitional to the non-biased direction, and then we make things equidistant for the definitional words. We make them equidistant from the non-biased direction, so they acquire the same semantics exactly. We have the same bias for each embedding vector. Okay, this is the encoder-decoder model I was talking about. We're gonna be inputting sequences from 1 to T to something called the encoder. And the encoder is just not taking an output at each time. Instead, we maintain the activation or the hidden state, or the high dimensional hidden state, the high dimensional memory. And at the end of the sequence, we plug this activation or this memory as the activation of another network called the decoder, and we started generating. So the decoder now, when generating y1, it will gonna be remembering everything from x1 to x2 to xt, and then generating y1. Then we plug y1 again, and the new activation, which knows y1 and things from x1 to xt, and we generate y2, so on and so forth. So this works in machine translation. So the encoder will gonna be processing the French tokens, let's say, and it will gonna be constructing an activation based on those French tokens, and then we're gonna be generating English words based on those, or this activation or this memory from the French tokens. We can do something called like image captioning, also an encoder-decoder approach. A convolutional neural network will gonna work as a encoder, passing a state or a hidden state to the decoder that we're gonna start generating tokens that are captions of this word. I'm gonna be introducing something called the attention model, very high level intuition, in order to make it easy for you to understand the transformer when we talk about it in the next time. So when processing a encoder-decoder architecture, we pay the same attention. We only take this activation after a sequence of tokens and pass it to the decoder, and good luck, start generating sequences. A smarter way to do it is to smartly pick up how much you need to attend for each of the activations in the encoder. So as we can see here, when processing the French sequence, we are computing activations for each timestamp. And when we decode tokens out in English, a smart way to do it is to pay attention differently for every input token activation, instead of just aggregating the full information into the decoder. So what we try to do is, when generating the token Jane, which is based on S1, we're gonna try to figure out some coefficients or some parameters, alphas, and those alphas are how much I'm paying attention when generating the token 1 at the input token 1, how much I'm attending to token 2 when generating the input 1. This is what's saying by alpha 1, 2, so on and so forth. So I'm gonna be scaling the activation for every input token by a parameter alpha, in order to look at some activations or some tokens differently than on others. The way we're gonna do it is that we're gonna assign some parameters alpha tt prime, and alpha tt prime will gonna tell us how much when generating the token t yt, how much I'm paying attention to xt prime. And specifically not xt prime, it's at prime, which is the activation at the timestamp t prime. And then when I need to compute yt, I aggregate all the information from at prime, which are the input tokens activations with their corresponding coefficients, into a summation, and this is now my state. I use this state to compute the output y1. And now you should be asking me, how we gonna figure out the parameters alpha tt prime. So since we don't know the function that's relating what to what when generating alpha tt prime, we're gonna assume that the function is a function of at prime, which is the activation of the tokens, and my last activation from the output, which is st-1, I'm gonna aggregate both into a neural network, learn this neural network separately, and then compute those those logits, and then doing a softmax in order to turn them off into a probability, and then the summation for these probabilities is 1, of course, and then I can assign every parameter for different input token activation to aggregate all the information and when producing the output. Okay, next time we're going to be talking about a transformer. This was a very fast, high-speed recap of our last lecture. I hope that you can enjoy it and really keep up with my speed.